Good morning, everybody. Hope you're all doing well. Great. You can hear me and I can hear you. We're off to a better start than last time. So it seems as if most of you are here. So let's go ahead and start. First of all, classical question with classical lack of answer. Was there any question from last time? Anything you wanted to ask? Or anything that was really weird when you went back to it and you would like to have a look at again? Otherwise, we'll pick up more or less where we left off with the exercise.
Olga?
Yes.
Hey, guys. Just a quick question. I believe Ira sent me also a message in regards your project. You will notice if you go through it that, well, Hazus does not exactly have the same classes as you would expect for a Greek building stock, which is natural.
Okay.
Hazus was made for US. Okay, guys? So in general, keep in mind that say that older Greek buildings tend to be of the, let's say, concrete and infill type. If there is a lower grade of that in Hazus, use that. I mean, lower quality or low code version of that. In general, you can consider older buildings to be concrete frame with infills. The reason being that they have small bay widths, okay, and generally small windows, small balcony doors, etc. So infills work with the frame. If you go to, let's say, mid-code, mid-era, like 70s, 80s, engineers got cocky and then they started increasing the bay widths. So funny enough, the buildings got worse and they have higher bay widths, larger openings, things got more modern. So let's say mid-code buildings are more like pure concrete frames. They have infills, it's just not that much of a, I mean, okay, theoretically, I mean, ideally we would have a perfect class that fits that era, but we don't. Usually the 70s to 80s buildings tend to fare worse than the 50s to 60s in many parts of Greece, okay? Assuming they were designed well, either way. And of course, if you go to the modern era, it's more like concrete shear walls. It's no longer concrete frames, because after 96, more or less, pretty much everything had shear walls inside. Okay, so for the modern ones, you should go to concrete shear walls, okay? And I don't know, I can't remember if Hazus has, again, mid-code, low-code, high-code, but, you know, similarly, modern buildings, high-code, older buildings, low-code, you get the point. All right, so that's it for me. Rest is up to you. You have any questions, because this is the last class, right? The last lecture of the season. You have any questions, feel free to email me about the project, Olga about what she already discussed yesterday, previous time and today. We'll be around, so no worries. The exam is going to be through internet, virtual exam, because if we try to have it live, they only give us an hour and a half. And in 1 hour and a half, there is no possibility of all of you presenting the project. So I already told everybody that it's going to be internet only, okay? So when we have the date, I will send everybody, I'm actually probably going to use the same. I just send a WebEx to everybody. It's the same, okay? So that's as far as announcements go for today. If you got any questions, let me know. Otherwise, well, I can proceed. We're good? Anything happens, email me, I'll be around. Olga, the floor is yours.
Okay, so thanks, Dimitri. So last lecture of the year, no pressure at all. Good, so I'll start screen sharing and see how that goes. Okay, so this is the second and last of our lectures, bringing ground motion from the base rock where you're used to it up to the soil surface through the shallow geological formations. So basically, as I said last time, though you're probably a bit too shy to do it, do interrupt if you want to ask anything, or if you would like anything repeated or explained, or if you have any thoughts to share. So I don't want this to be a purely one-way thing. So we've established I can hear you this time, which is good. So feel free. Last time we started with a few keywords, and we've spoken about most of them already. And we're gonna delve deeper into our table of contents. I don't know how far we'll get, because I would rather you understood better than got to hear more. If we make it to the end, we'll make it to zone nonlinearity and dynamic sort properties. We'll see how that goes. So as we did last time, if you would like to go to kahoot.it, we can start with a short little poll to wake you up with some groovy music and revise a few terms and introduce you to a few terms. So I'll try and generate the pin now. Okay, so if you can now see that, just go to kahoot.it, and 752479. So let's start generating our list of players. And since only half of you participated last time and you saw that nothing bad happened to anybody, maybe you want to participate this time and see how you do. A few brave people using their real names. Only women so far. So this works on your mobile as well as your computer or tablet. So let's get started. So do I only get Sol amplification between layers if there's a change in material stiffness, or can there be other factors? All right. So, do you guys want to tell me what are the other factors? Just feel free to switch off a mic or write something in the chat box. Antonius, what did you vote for?
False.
Sorry, false. Okay, why? Tell me. What else might there be other than change in material stiffness?
That is my thing.
Sorry?
That's my thing.
Okay. Mia, Ira, from the folks I remember. What else? What other mechanism might there be?
To be honest, I think I didn't understand well the question. So
Okay, I think that's probably it.
And also, we can see these questions do not appear in our screens, at least in mine.
I know. Your device is just to answer yes or no, and the question is on the main screen on what I'm sharing.
Okay, thank you.
Okay, so this was just a short revision from where we left off last time, and we're going to pick up at this point today. But basically, the number one key factor that causes amplification in the way we're going to talk about is mostly a contrast between shear wave velocities. So I would have expected more of you to say yes. So let me see where the next question is. Okay, so VN was the person who got it closest. So if you're on a hill or slope or ridge, where do you expect the shaking to be stronger? At the toe, so underneath at the bottom, at the crest, meaning on top, along the flanks, or does it not matter? So greatest amplification, strongest shaking. Okay, awesome. So that's correct. So it's at the crest, and we have quite a bit of variability along the flanks. And I'm really happy that none of you think it's all the same, because it's really not. So the surface of the ground really, let's say, distorts and lends its own personality to ground motion. All right. So imagine an 80-meter high reinforced concrete building. You have a little more time on this. So if you were to assume that it works a little bit like this, the lollipop assumption, right? What is its oscillator period? So its fundamental period of vibration. Imagine 80 meters, and you know how many meters roughly is to a story. So just give me a very rough ballpark idea. So I've given you a huge range from 1/10 of a second, which is 10 hertz, up to 10 seconds. No answers? Be quick. No, yes answers. I just couldn't see them. Okay. So that's funny. We're torn between two values which are different by one order of magnitude. That's interesting. So when we get to that slide where we say more about it, I'd like to hear what you guys were thinking of. Does anybody care to stand in a soapbox and defend 10 seconds for me? I would accept it if you were thinking I were talking about perhaps 80 stories. So 80 meters is not so many stories, right? Okay, let's go to the next one. We'll have a plot showing you that sort of relationship, and we'll come back to it. So I don't know who these two people are, but up to now they're the champs. Let's go to another one. This is easy. So I know who this man is, and he is awesome. True or false for each of you? Okay, I'm really happy. So, by the end of today, I hope the red one person will know who he is and will be convinced that he's awesome. So that was Joseph Fourier. So the Fourier spectrum we're gonna have a look at. So HF is on fire today. Next one. 2 questions to go if you want to tilt the scales. So when I have very high amplitudes of ground motion, very strong shaking, what changes in the soil properties? We have stiffness, which may go up or down, and damping, which may go up or down. Which way do you think it goes? Only a few seconds more. All right. So I should have said you can choose more than one things. So, okay, the number one feature I would say is that stiffness and shear wave velocity decreases. A few of you got that, but none of you got the damping increase. So you may not have done a lot of soil dynamics in your backgrounds. If we have time in the last few slides, we'll go over that. That's basic soil dynamics. So if you've heard of G gamma D curves or stiffness degradation curves, so stiffness degrades and the attenuation or the damping does the opposite. So it goes up when you have soil nonlinearity. Scales have tilted. Okay, HGT. And one before last chance. What kind of spectrum is this? A design spectrum, a response spectrum, Fourier, or not a spectrum at all? Just a few more seconds. This is a quickie. Okay, very good. So it's a response spectrum, and we're going to go over the difference with the Fourier. So I'm happy there's none of the design and now the spectrum answers. So Fourier is awesome, but that wasn't his spectrum. Okay, it's between HF and HGTE. And very last one. This you may not know, so you can guess. So if I'm looking not at an acceleration, but at a displacement recording, a time history, is it messed up by low or high frequencies, or does it not care? Quick, quick, quick. Okay, amazing. I thought that was the hardest question, but you got it the best. Yeah, it can be messed up by low frequencies, and we'll have a quick look at that too. Okay, who was HF, by the way? Well done to all of you in any case. Okay, so I think the sonolinearity one was the hardest one. I'm guessing because it wasn't in your background. We haven't taught this yet. And I think the first one was probably poor phrasing. So I'll put this away. And try and minimize all the rest. Okay, I'll keep the chat in the background if anybody needs to tell me anything. So we've been talking about site classification, and we went over the Eurocode 8 classes in painful detail, I'm sure, for you. So we've had a look at the average, the VS velocity over the first 30 meters. And we've looked at different types of soils and different types of mechanisms for shear strength, like cohesion and angular friction, differences between sands and clays, the notion of looser and denser soil, SPT, which is the standard test you do when you drill a borehole. And we've sorted out how to classify profiles based on these. So one key clarification to begin with. So we often say soil classification, but we really mean site classification. So we're not classifying any one of the layers in the profile, but the profile as a whole. So I'm classifying, I'm trying to understand what's going on with a certain location where I need to perhaps build something. So we're leaving soil properties as individual personalities of different layers, and this is trying to mix all of them together and derive a kind of mean class for whatever you have where you want to build. So we had a look at how the design spectra vary with where you are on the map based on what kinds of sources you expect to have near you and whether these sources can give you big earthquakes. So this is the difference between top and bottom. And within each of the two panels, we spoke about the difference between the different soil or site classes, A to C, according to Eurocode. And we've said already, and we've seen some examples of spectra and of time series. I told you that we can see effects of the soil, of the local geology, and the time domain, and the Fourier frequency domain, and in the response spectral domain. So because sometimes folks can get confused between the two. So here I'm showing you Fourier spectra, although the x-axis is period, it might have been frequency, so the reverse. And here I'm showing you response spectra. So the axes say that, but if they didn't, I wonder if you would have sorted out which is which. So this was one of the questions I asked you in the Kahoot. I showed you the definition of a response spectrum, and almost all of you got it right. So if you're confused, usually the Fourier is the response spectrum is the neatest one. It's by definition the smoothest, the nicest one. Both of them can be computed if you have a time series available. So the input to both can be exactly the same thing. You can have an acceleration time series and you can compute one or the other. They mean different things. So I have a few slides to remind us of what they mean, and that'll be right after we finish off where we left off with the 1D soil amplification. So we left off here, and we had a very simple soil profile. Basically, we had an ideal soil profile where we have a single layer that's of course homogeneous, etc., on top of the the rock, which we consider as an ideal half space. So here we have only a simple case, one layer. So it's a soft layer, it's got a low velocity, and it's on top of the rock, which has a high velocity. So we said that basically the depth or the thickness of the soil layer is what virtually determines the entire profile's resonant frequency. And I don't know if you ran through the exercise on your own since last week. I'm gonna bet no, unless anybody says otherwise. And we're gonna have a quick look at it together today. So the resonant frequency is the simplest formula ever. So it's Vs over 4h. So 4h could be going up and down twice for these poor trapped waves that you have here. So you have your thickness of your soil layer over bedrock. So we solved for the frequency last time, and the period is obviously 1 over that. So we had about how much? Okay, so Hamdi wrote to me that he was the champion, I think. Okay, so well done, Hamdi. Okay, and I think you were the one who gave us the number from last time. This time I have a calculator so I can do things with you.
Yes.
Here we go. So what would you say is the fundamental period here? Oops. Okay, would 6 hertz be correct? Does anybody disagree with 6 hertz? Okay. Do feel free to unmute your mics if you ever want to. Okay, so 2 folks saying it's 3 hertz. Thank you, 2 people. Rest of you have probably elected them as your class reps, but I'm hoping that you guys are doing it at home too. So we have the resonant frequency, 3 hertz, and what we call the higher modes. We can find them stupid easy by going 3, 5, 7, 11, etc. Of course, what we said last time, and I'll remind you this time, is that depending on what this first number is, which was here 3 hertz, is going to kind of in a way define how many of the higher modes you care about. So you usually have an idea of what kind of range of frequencies you're interested in. So for typical structures, I remember at least I was taught we were usually interested in 2 orders of magnitude from 0.1 to 10. Hertz or seconds, it works either way, of course, right? So if, for example, you get a resonant frequency of 3, then you can fit 3. 3 times 3 is 9, 5 times 3 is 15, and then you get to higher modes, higher frequencies, 20 hertz and above. So you can fit 2 and maximum 3 interesting peaks within your overall frequency range of interest. Now, if your resonant frequency had been 0.5 or 1 hertz, then can you imagine that you would have many more interesting peaks within the same range? You would have 1, 3, 5, 7, 9, 11. So you would have like double the resonance peaks compared to what you have now. So depending on where you find it, it might be the main one that you're interested in, the main feature, or you might also be interested in some higher ones. You note here that the higher ones have lower amplitudes, and that's most often what happens. Now let's try and see how much the amplification is. So we basically, we're trying to define this function with frequency. So x-axis is frequency, we've seen that, and the y-axis is amplification. And let's just, so I'm hiding the numbers here for you for the time being. We saw that the numbers here, you know them. We found it's 3, 9, 15, etc. So I'm hiding the numbers here, but can anybody tell me what number we begin with? So what is the value of the x-axis here, where I'm pointing my mouse? Can anybody venture a guess? Where do we anchor this function, which is basically, we call it the transfer function or the amplification function? So where we start, and it's basically, we kind of end up here, and at the end we end up there. So we're kind of moving around this key value. What would this reference value be? What are your usual reference values? From what I remember, they can be 0 or 1 or some other like typical value. Do venture a guess. Okay, thank you. 1, 1, 1, 1, 1, 1, 1, and we agree. And in case anybody was tempted by the value of 0, we're gonna see in a bit why that's not true. Basically, this amplification function is a ratio. So it's giving us how much more ground motion in terms of amplitude do I have at the top of this surface layer, at the top of the soil, with respect to what I would have had if this rock continued up to the surface. So it's a ratio of the ground motion here after it's been filtered through the soil with respect to the ground motion more or less inside here, inside my infinite bedrock layer. So it couldn't be 0 because you will never basically kill all of the motion. You can amplify it, you can de-amplify it a little bit, but the effect of the layer is gonna be basically going around unity, because we're talking about a ratio. We're not adding and subtracting, we're basically multiplying. So the 0 would mean that at certain frequencies, so some points along the x-axis, we would be killing everything, and nothing can do that so efficiently. So this is correct. Our reference value is 1. And actually, if I were to walk along this profile and find myself at a location where this rock formation outcropped, so let's say the soil is the filling of a basin, and I walk to the edge and I go past it, and now I'm standing on rock. What would this look like if I were standing on rock? It would just be an horizontal line at 1, because it wouldn't be amplifying with respect to itself. We would just be seeing its own response. So we're looking at what the soil does with respect to the rock. And the key properties which are going to anchor our transfer function along the y-axis. So we sorted out the x-axis, so left and right. Okay, this is defined basically by the Vs of the soil and the thickness of the soil. Now we start caring about the rock. When we need to anchor our results in the y-axis as to the amplification level, we start also caring about the rock. Up to now, you only needed to ask how deep is this layer and how slow. Now we care about how slow is it with respect to what's underneath. So how much faster or stiffer is the rock compared to the soil? So this is why we have this ratio. So VS2, so the big VS, the rock VS divided by the soft one. And if you have the information, you can also add the ratio of the densities or specific weights. So in soil mechanics, you call it gamma, you know. You can have 18 for the soil, you can have 21, for example, for the rock, or a bit, this is a little bit, or rather, very much heavier because it's an imaginary, very, very hard rock, which you would normally find at a deeper depth. So if you don't know your densities, you can just get this contrast, this impedance ratio, by dividing the two velocities. And you can see down here that the amplitude depends a lot on this contrast. So this is basically telling us that we might as well have this contrast on top. The stronger the contrast, the higher the maximum amplification is going to be at the resonant frequency. So A0 is the amplification at F0. And you can notice here that there's another little thing added here in this ratio, and this is the damping. So this is the damping of the soil. Obviously, we mean the damping of the soil on top, because that's the layer within which all the waves are trapped. And it's his or her damping which is going to affect the maximum amplification due to the trapping, the resonance of these waves. So the engineers typically think of a percent damping ratio. For example, here you see 5%. And just to bring it into seismological and geophysical terms and come full circle, this can also be given as Q, which is the quality factor. None of it has any dimensions or units, of course. So a quality factor of 10 would be 5%. They're just joined by one is equal to 1 over twice the other. So 5% is 1 over 2 times 10, etc. We had 2 examples in this little plot. So for a higher quality factor, which is basically a smaller percentage of damping, for example, 2% rather than 5%, if your damping is lower, this is going to be higher, right? So if you had no damping at all, which is not possible on planet Earth, you would basically have this resonance asymptotically going to infinity. But of course, you never have that. It's capped by the fact that any kind of motion is attenuated on Earth. But this is the way it goes. The stronger the attenuation, the stronger the damping, or the lower the quality factor, the more you cap it. So instead of having this maximum value, you have this one. And you can go through the motions of computing this for both of them. Okay, this we already said, it's a very trivial calculation. I don't want to waste time asking you to do it. So I just gave you 2 very typical values you would have heard of if you've done soil dynamics before, which now I'm not too sure about. sorry, 1%, my bad. So you can see how the difference in the damping gives us a big difference in the amplitude. So let's just go for a rough estimate of the contrast here. Let's just ignore the densities to make it easier. What if I showed you this? So 350 over 2500. So basically you would be trying to do this ratio, okay. And actually the inverse of this, because you would put the fast one on top. So it's basically 250 to 35. So that's roughly a contrast of 7. And just so you know, this is a very, very high contrast. So this is just an educational example. In nature, you will almost never find such a high contrast. But this very high contrast, especially if it's not accompanied by very strong damping, it's going to give you a very high amplification. So if you go through the motions, at home, you're going to compute an amplification of about 5 for the strongly attenuating material scenario, and an attenuation of about 9 for the not so attenuating scenario. So I want to just pause for a few seconds here and make sure we all understand what this means. So this is a ratio. So it's telling you that if your rock went up to the surface, so we said this line would be just an horizontal line at unity. And the deviation from unity is giving us the amplification that this extra soil layer is adding to what the rock would have had it be. So this is saying that because of this silly little 30 meter, 350 meters per second slow layer, you might risk having 5 or 6 or 7 times stronger shaking at 3 hertz. And at 9 hertz, so the second peak, it's smaller. So it could be from 3 to 6, depending on the damping. You already notice, I hope, that for the higher modes, so at 9, 11, 15, etc., all of that, 21, sorry, not 11, etc., you have a stronger difference between the top and the bottom values. And this is how it usually goes at higher frequencies. The damping plays a stronger role. And for the lower frequencies, it plays less of a role. But you can already see that you also have some amplification at 9 hertz, not just 3. So if you had a structure up here, it would feel much, much stronger shaking at these particular frequencies. And these frequencies depend on how deep the soil layer is and how slow. So they depend on the H and the VS that we saw. And how strong the shaking is, so how badly it shook, depends on the contrast, the ratio between the VS of the soil and the rock. So now we were able to basically anchor on the x-axis and on the y-axis. So if I were to play around with the parameters here, and if I told you that we have the same materials, but I walk and I get to a place where this soil material is deeper, the basin deepens, and suddenly I'm standing somewhere where I don't have 30 meters underneath me, but 60 meters. What would happen? Would the peak shift up, down, right, or left? And I would like you to type in your answer, at least a couple of you, to spark the conversation. So looking at this thing here, does it go up, down, right, or left? It's going to shift, that's for sure. When we go to a deeper layer rather than a shallower one. Is there anybody who thinks it shouldn't shift? Okay, left. Okay, thank you, George. Does anybody disagree? Of course, he's done all the dirty work, so you don't have to, do you? So left means it's going to shift to lower frequency, which means longer period. And that's exactly right, because when you get a deeper layer, you can just imagine the waves. The waves are trapped. They're going to be traveling double the thickness, double the distance as they're trapped. So there's no way this is going to become faster. Faster would mean higher frequency. So if they need to travel double the distance, this means that we're going to shift to exactly half the frequency or double the eigenperiod. Right, period is 4h over Vs, so double that. Thank you very much, George. Obviously, if I walk the other way and I find myself where the layer is shallower, the shallower and shallower the surface layer becomes, the faster those little bastards can go up and down, right? So it's gonna be more high frequency. They can cover more distance faster. So they can go up and down twice as fast or 4 times as fast as you go divided by 2 or 4, etc. So that's gonna push your peak to the right in exactly the same way. And if I decreased the difference between these two, 350 and 2500, if I now told you that, you know, we ran geophysics and the bottom layer only has a VS of 1000, it's soft rock, softer rock. Where would you move the peak, up or down? Okay, thank you for playing, but it would move down. Why? Because we need to think of the ultimate extreme case. The ultimate extreme case is those two become the same material. If the difference between them is minimized, then the extreme scenario is one horizontal line with amplitude 1, right? You all told me that a few minutes ago. So in order to deviate from unity, I need the contrast between the two materials to become bigger and bigger and bigger. So the contrast here was 7. And you see that the amplitude, the amplification is more or less, it's close to 7. If I decrease the contrast, and if I say these two materials are more similar to each other, the peak is going to come down. And if they became too similar, if they happened to have the same VS, all of the peaks would come down so much, we would be looking at them down here, close to unity. Does that make sense? Now, so thank you, Maria, for trying. And hopefully this has clarified it. So bringing the contrast lower is what's going to kill our amplification. So the more different the layers, the more screwed we are, because it's going to generate higher ground motion at the surface with respect to the rock. And why do you care? Because you have been trained for a semester, and you've been trained by the best, by the way, to compute ground motion mostly at bedrock. And I'm only telling you about how to bring that, take it by the hand and bring it to the surface. So if that surface layer is very, very different, much, much softer to your conditions at rock, then it's going to bring your ground motion much, much further up, which is a bummer. And the only thing that can kill it, to bring it from here to here, is the damping. But the damping of your material is what it is. You can't change it, of course. So the bottom line And it's worth it taking these few slides slower if it's going to help everybody get on the same page and understand this, because this is like the heart of these entire two classes. The bottom line is that all of this mess is caused by this layer overlying the bedrock. So this makes the ground motion frequency dependent. So you don't have something like this, you have something like this. And where you anchor it depends on what we said. So it's frequency dependent. And if you compare this to what we said about what the design codes give us, or how you look at PSHA, hopefully you can get a feel for how much this, whatever we have on top, can mess things up. So when we looked at how we use the design spectra, so the design codes, we said that based on what material we have, A, B, C, D, E, this just pushes our design spectrum up or down a little bit. The plateau goes up or down a little bit, and a tad to the right or left. So we pulled its ear a little bit to the right to accommodate softer materials. I don't know if you remember, but this plot in the Eurocode, if this is soil A, then B, C, D, E moves up and to the right. It's amplified and it covers longer periods. So this means a shift to the left in the frequencies. It's what George replied for me a few minutes ago. He said that if I make it deeper, and also, by the way, if I make it softer, this is going to move to the left. So shorter frequency, longer period. So these things are going in the same direction, obviously. So the codes are informed by these basic physical mechanisms behind amplification that I'm teaching you. But I hope that you can now feel how inadequate this design spectrum can be on occasions where we have a strong impedance contrast and high amplification and very strong frequency dependence. Because this is only upping us by 20, 30, 40%. You see, up to 1.4 with respect to rock, 40%. And here you can see that at certain frequencies, not PGA, but certain frequencies, the spectral amplification can be much higher. So now I want to come full circle and connect this to buildings. And most of you know more about buildings than I do. I did my earthquake engineering almost 20 years ago. So you've been taught a lot more in this master's than I was in my undergrad. But a few of the very rough rule of thumb relations to bring together structural response with soil response. And I'm sorry, because in this slide, I think oops, just a sec. This annoys me, so I'll just bring it back. All right. So this is where the soil will affect the building the most. And if I ask you, which kinds of buildings would be affected the most by this, what would you say? I personally would go back to this formula because it's the only one I know by heart. And you'll probably guess that we're starting to get into the Kahoot question of what is the eigenperiod of an 80-meter tall building made of reinforced concrete. So what I always have in mind, even if it's very, very awfully rough, is this rule of thumb, which is number of stories divided by 10, and this gives us seconds. So let's just run this through the Kahoot example. I gave you an 80-meter high building. How many stories to an 80-meter high building? What is your typical assumption about story height? Very, very rough. for the kinds of buildings we have in our country, at least. So for the folks in other countries, I don't really know how, they build there. But how many meters is to a story here, roughly? I don't know. Look at where you are. How many meters is it to the ceiling? Okay, Vasiliki says 3. Anybody have something very different? Ah, very accurate. 2.7. Okay, George, thank you. And Ira is the reconciliatory force here, so joining the 2. Thank you. So I'm gonna go for 3 just in order not to need to do harder math. So 80 divided by 3, you can probably do it in your own mind. I'll do the 2.7 with a calculator just so we have a ballpark value for that. So that's giving me 30. Okay, 26 to 30 roughly. And that, if you divide it by 10, you get more or less 2.5, 3, something like that. So the taller it gets, the more it deviates. If you had a 1-story building, typical value we might think about is 0.1 seconds, so 10 hertz. So very high frequency, because the really short building, it's just gonna kind of grasp onto the ground and move with it, whereas the very tall one is gonna move quite differently, and it's gonna be able to, let's say, sway more, if I'm being very loose with my terminology. And what I recall as a rule of thumb is that, roughly 8, 10, 11 stories might be around a second or more. There's this other pretty old relationship by some folks at the Athens Uni, which gives an alternative, and there's been a lot more since then. I found a couple of papers which are more recent and done by a guy in Lisbon who I know is rather good. So he did micro tremor measurements. So he's tried to do it not just with simulations like Abacus or whatever, but also go into real buildings in Lisbon and measuring. So there's a few more relationships for you. So he's also done it for the transverse and the radial component of his buildings. You can have a look at the papers if that's something you're more interested in. But I was interested in just compiling a few of the existing relations just to have a look at what they look like. And this was his data set. So this is how many buildings he had. So 100 something, we said, from different decades, including a lot of 95, 2000. So this is reinforced concrete. And the 2 directions, longitudinal and transverse, so the 2 directions of the building, the periods in those directions are pretty well correlated. So this is what this shows you. And the results are basically this cloud of points. And this is the correlation between the eigenperiod and the height of the building. So basically, in my question in the beginning, I was just stealing, and I just said, okay, 80 meters, what does Oliveira give? Around 1 second. So I just stole it from him. But the very rough rule of thumb would have given you a slightly different value. Not 10 times higher or lower, but 2 times for sure. So this is a linear relationship, or we can derive a linear relationship. I love that they say removed outliers. So anything that doesn't fit, we just throw it away. Okay. So this is a pretty good correlation. It might have a coefficient of maybe 70% or something. So you're entitled to give people an equation. If it was a cloud of points like this all over the place, you wouldn't be entitled to give the equation. And this is just an additional thing I wanted to tell you. Well, it's not a fun fact, it's a sad fact, but just a fact. And I love that he tried to do that. He actually thought of comparing like community housing, what they give to the poor social strata, with like richer folks' homes. And you can see that the data plot differently. They plot parallel, and the poor folks' homes are the black dots. And because the walls are closer together, because they're entitled to live in small rooms, they don't give them a lot of space. That actually lowers the eigenperiod of the community structures. So I just wanted to just leave that in for you guys to ponder on it, if you will, later on. But in any case, my point was what? Depending on the fundamental period that we computed for our site, depending on the thickness and the velocity of the soil, we can kind of gauge which structures will be more sensitive. For example, we computed 3 hertz, which would be, and some of you gave me 0.3 seconds. This is somewhere here. If I go here, and actually I won't go to the line, I'll go to the data. I'll go to the data points. Those are always better than the model, the line. Data is better than the model, of course, because it's the real thing. So if I had that soil layer in Lisbon, and I had 3 hertz, I would go here, 0.5 seconds, and I'll leave the full screen mode just to draw it for you guys. I would do this. I would draw a rectangle, let's say 0.3 to 0.35. And whom does this affect? Can you see? It's all of this data here, basically. So you can see that it affects buildings from, let's make it bigger now, I don't know, from 17 to 20 something stories. Okay, if I do the rule of thumb, it would be eigenperiod is number of stories by 10. So 3 hertz, 0.3 would come from 3 stories, and 3 stories would basically be 10 meters. Well, the Lisbon data is kind of doubling that. But you can see, so the main thing is that a skyscraper wouldn't care. A skyscraper is here, right? I mean, I don't even know so many buildings in Greece that are so tall, or if we have any. We probably have. But they're up here. They care about what? 1 second, 1 point something or minus. So they care about these kinds of periods. So in frequency, this would be 0 point something to 1.5 hertz. So they care about a much deeper, softer soil. They care about longer periods, longer wavelengths, and it makes sense, because this swooning motion that the tall building will have is going to resonate with a deep basin with slow waves going up and down slowly, taking their time to resonate, whereas the short structure is going to resonate with these faster trapped waves, which are going to go up and down, up and down, up and down pretty fast, because they're in a faster and less thick or shallower material. So I want you to try and put all of this together to come full circle and correlate the kinds of structures and the kinds of soil profiles we talk about, because the worst case, as happened in Mexico in '85, as you were told already, is when we have this double resonance as we did, and we had that at only 0.5 hertz, so 2 seconds. You can see here this crazy response spectrum at 2 seconds. This is soil compared to rock, which is not feeling anything. So buildings on rock were fine. Buildings on this soil, I mean, these buildings didn't care so much. Those buildings didn't care so much. These ones did. And these are the ones that had eigenperiods around 2 seconds. So roughly, with a rule of thumb, 20 stories. So let's say 10 to 30 to give a very rough range. But it wasn't my grandma's single-story building, because that would have been here. That would have been short period. And it wasn't, because Mexico also has like some huge torres, towers, and those would have plotted here. The ones that cared, the building stock that felt it, were the buildings with those particular eigenfrequencies. So roughly 2 seconds. So this is why I apologize for this. This is why I drew those little glasses for you, because it's all about the kind of glasses that your building is wearing, what kinds of frequencies it cares about, and the kinds of glasses that your soul profile is wearing. So the kinds of frequencies that it cares about. And if you have, for example, as we had in Mexico, a big earthquake recorded very far away. That means the big earthquake created long periods. It's rich in long periods. They traveled 400 kilometers. So the high frequencies died anyway. We said they're like, you know, the impatient child jumping up and down, and it's going to get tired real soon. So the high frequencies get tired real soon, and the slow, long periods survive. So in the center of Mexico, it was the long periods that survived. And they went through the rock, which didn't care because it had a different pair of glasses on. And then they went through the city center and near the Zócalo, where you have the old temples, etc., the old lake. And that's where these long periods went through these deep, soft alluvia. So they were amplified a hell of a lot. So you had the first resonance with the site, small Vs and big H. See, tiny Vs and thick material. And then the double resonance was these were long period waves were amplified, and they started looking at the building stock. Which buildings were the victims? The ones that matched the glasses, the ones that matched half a hertz or 2 seconds. So with this very rough rule of thumb, n divided by 10, 20 stories. And because I say wavelength a lot, and we're gonna see a little bit of that, wavelength is what? Is distance. Distance is velocity times time, right? Because velocity is distance divided by time. So this is the equation for your wavelength when it's going through a particular material. If you have, if you have a material with a particular velocity, like any Vs you want, at a particular frequency, you can have a particular wavelength. So this is how these guys are tied together, in case you hadn't realized or you'd forgotten. So in Mexico, this is what happened, where we had 40 or 50 meters of this particular soil. We had this resonance with which buildings? The ones which were tall enough to care. So we saw these response spectra in rock outside where the uni is. If you ever get the chance, it's the most beautiful uni in the universe, Unam. So here, people didn't even feel it maybe, or they felt it very little. At the center, in Zócalo, this is what happened in the time domain. So you see this very persistent period, because you can see that the zero crosses are coming, they're equidistant, right? This means that in the frequency domain, we're going to find them at one particular frequency. And you can see, of course, the difference in the maximum amplitude in the PGA. So in all of these domains. Now, I think I'll have a 10-minute break because we're a bit behind what I wanted us to be for the break, but I don't want your little brains to get over hot. So let's take 10 minutes and be back at 1:15 tops, if that works for you.
Okay,
and
thank
I'll
you.
unshare until then. All right. Hi, everybody. Okay, let me pull out the chat again. Okay, so we were here. Okay, so we looked at one-dimensional amplification, which is the heart of the matter, but nature is complex, and very often there's additional constraints and additional conditions. So for example here, I was telling you before, what if I walk and I find my soil layer gets thinner or thicker, etc. This basically means that I'm deviating from the one-dimensional assumption, which we were making to do the, 4 times h over vs, etc. We're deviating from this one-dimensional assumption of waves going like this, and we're looking at also waves traveling any which way. So what happens when we get to the edge of a basin, for example? Then everything is no longer horizontal. Some things are inclined, so layers are inclined and like the basin edges. So our seismic waves generate additional waves, and they generate a lot of surface waves, so Love and Rayleigh waves. And those will often tend to propagate horizontally and move towards, for example, the center of our basin, and they're going to meet other ingoing waves and make all sorts of complex wave fields. So there's a lot of phenomena involved. So they're reflected, they're diffracted, etc. You can often find damage concentrated along such edges. Like this was the first example that was ever recorded by a scientist in a paper from the Kobe earthquake in Japan. And imagine if you have a smaller basin that is really severely not one-dimensional. So this, for example, the Grenoble Basin, it's got varying basement and different inclinations at the edges. So imagine all the waves coming in and saying, whoa, this is really not one-dimensional. So the new waves are created and interfering with the incoming waves any which way. So the interference can be what we call constructive, creating more amplification, so bad for us, or destructive, which is actually good for us in the structures, because that might de-amplify. We're not going to go into like heavy physics or any equations, but just so you have an idea based on the physical understanding you now have of the one-dimensional situation and the trapping of the waves and the reflections and the transmissions, imagine having all of the additional ones coming in because of the 2 or even 3 dimensionality. And of course, this was all what's going on underneath. And we also have what's going on at the surface. So if we have topography, and that brings us back to one of the Kahoot questions, we tend to have amplification here at near the crest, and de-amplification or minimum amplification here close to the toe. This is you see it in the as a whole time series, and here you see like maximum values as you move up. Like imagine walking up the hill, and you can feel stronger and stronger amplification. So there's focusing and defocusing of waves going on, and diffractions and all of those things. And there's 2 very simple empirical relations that can help you guess at which frequency things are happening, because as happens for the 1D, and it's much more the case here, things are frequency dependent. So if you're at the top of the hill, you're going to feel amplification mostly at certain frequencies. Which ones? There's these 2 relations here, and I've drawn it out for you to make it very, very easy. One relation is by Ashford and Seeter, and they say that there's amplification, well, maximum amplification over a wavelength, which is roughly 5 times the height of your slope. So I've drawn for you the height and roughly 5 times that. So this is the kind of wavelength that the waves would care about and get amplified. So not something very, very small. So you can imagine that this is something that's not so high frequency. And if I were to say that this is made up of a sandstone with a velocity of 900 meters per second, and you have a 1-to-1 slope, so 45 degrees, and it's a 30-meter high slope, then what would be the frequency, so the F topo, according to these guys, Ashford and Seeter, they're at Berkeley, California, what would be the frequency at which you would have the amplification? How would you go about it? You would think back to the definition of the wavelength, hint, hint, that's why I gave it to you before, and you would say, okay, what is frequency? Frequency is distance over wavelength. I know the wavelength, it's 5 times h. So I know it because of the geometry. And I know the Vs, so I know the properties and the geometry of the slope. And so I can do what? I can do a Vs of 900 divided by my lambda, which is 5 times my height. And that's going to give me what? Well, whatever it gives me, 935. So I'm getting an F topo of 6 hertz. And I hope you do too. Don't see any answers. Okay, the last answer was yes. Let's have a break. And the second way to go about it is to use another empirical relation by Gély et al. So those are French folks. And they say that, oh yeah, but we also see an amplification at a wavelength comparable to the topographical, well, to the hill or to the slope representative length. So for the hill, this would be like the half width. For a slope that then goes on like an embankment, it would be the entire length. So give me a number in hertz for this little example. Let's have a few seconds to do this. So again, if I were to ask what is the frequency of topographic amplification, according to these folks, for exactly the same configuration, you would need to compute your width based on your slope and your height, and revert to your lambda equation. So what would it be? It's stupid easy, but just to keep you going. Okay, thank you. HF again, there was a reason he was a champion. So, 30 hertz. So that you all can already see that maybe 30 hertz, we don't care so much for regular buildings, but 6 hertz, maybe we do, right? So this is the higher frequency and the other was the lower one. And in which direction is it strongest? So if you want to know if the dashed lines are the axis of your ridge or your slope, then with respect to your axis, it's going to be the perpendicular dimension, dimension, direction, that's going to have the maximum amplification. So you're also going to see an amplification as you're, let's say, walking along the top of this really scary ridge. But as you're walking, the shaking is going to make you move left to right more than it's going to make you move, you know, front back, if you get my drift. And how far from the crest does it happen? So this is just a numerical example from my thesis. So this is about Aegion, a city in the Gulf of Corinth I showed you before as well, because I had the data. So this is what happens to the maximum response of my model as I move farther away from the crest. So this is the crest, and I have my maximum at a few meters from it. So this is roughly 20 meters or something, 30. And it goes out to 100 perhaps. And you can see that there's two directions, SV and SH, and SV is the one perpendicular to the axis. SH is like this, it's the axis. So if you're walking along, so perpendicular to your screen, if you're walking along the edge of the cliff, the topographic amplification in case of an earthquake is going to make you again move right and left more, and this SH is going to be less. At which frequencies? If this is the topography, because this was the model for Aegeo, and I invite you to do the calc, so it's 5 times the height and 1 time the width, you will find it around 2 and around 5 hertz. I also found a higher one, but I didn't get around to proposing a relation. But these are accepted relations from the literature, the ones I just showed you by Ashford and by Joly. And you see that the numerical model indeed gave us topographic amplification factor there. So this is a factor, so it's just like we had the transfer function. So it's a division of something far away with respect to something near the slope. So this is how we quantify that the diverging from unity is amplifying. So we had an amplification. This is around 50% in log scale. This is 100% amplification factor of 2. And what do the codes say? So the Euro code, which actually, I'll show you this first because the French are the ones who thought of it first. So late 80s was the research by Joly. 95, the French design code had already picked up on it and proposed something. So this is pretty awesome because usually you don't have only 6 or 7 years between research results and the code design committee saying, yes, sir, we're going to look into that and apply it. So you have a little bit of an explanation here. I just copied from my thesis because I don't have the original text and it's going to be in French anyway. And this is showing you, this is your cliff. So you can walk here, go up the cliff, and maybe it's horizontal, or maybe it's got an inclination, little I. The inclination of the main cliff is the capital I. Height, that's important. And near the toe, you have an amplification of 1. At the crest and behind it, you have a maximum amplification of, we say taf, in English it's called tau. And after a certain distance, it ramps down and then you have 1. So if you're very far from the crest or if you're at the toe, it doesn't give you an amplification. The maximum is behind the crest, and you saw here that the results actually confirm that, of course. And what's the maximum value you can have? It depends on your geometry and on your inclination and your height. And the maximum is 1.4, 40%. We already saw here that 40% works okay at 2 hertz, and I saw higher amplification at the second frequency by Joly. So around here. Okay. And the Euro code, which years later stole the idea from the French code, gives something which is a bit more vague. It says whether you have a closed or an open geometry, so cliff or ridge, what's your inclination in degrees? Less than 30 degrees, don't do anything. Sorry, less than 15 degrees, don't do anything. 15 to 30, what's your height? If it's less than 30 meters high, don't do anything. I kind of disagree with that. Is it up to 30? Then you can take a 20% rise. If it's more than 30, if it's like this, 30 or more, like A here would be, you can take 40%. So again, same maximum. It's capped at 40%. Where? No idea, dude. So at the top, so at the bottom, it's 1. You can ramp it up as you go up to the top. And how far behind the crest? No idea. What frequency do I do it over? All of them. No idea. Whereas you see here that it's very frequency dependent. It happens at very particular frequencies. And if we know the slope, you can compute it. You can already do it here. I have the answers for you here to compare if you want to do it at home. So it doesn't take into account the frequency dependence, but it does take into account a bit of the research, and it caps you at 40%. Your actual amplification might be bigger, but that's life. It's a step in the right direction. This is just a comparison between the two. And if you wanted to apply it, this is again how I try to do it for my thesis for AHEO. So these were my results. The black and the red is what you saw before. So maximum amplification from my numerical 2D model going out to, this is 100 meters. So maximum was around here, out to 20, 40 meters. How would I do it? This is what the French code said here. And this is what the Eurocode would have said, and I need to decide how far out to bring it. So to do this, I would have brought it out by, say, 50 meters or whatever, and ramp it down however I think I should. This would have been guided by my numerical models. If I don't have those, the code, the Eurocode would only give me this number, 20% or 40% if it had been steeper. And that's it. So a lot of it is up to you, how to interpret and how to apply. So regarding all of these, there's going to be a little extra credit exercise for your final paper, which you'll receive soon. And I'm sure your faces are looking like this at the moment, but it's the only way to make sure that you're going to try and do a little application. And I'm gonna move, to the next set of slides and pick up where I left you off in our previous, in our first hour, where I was trying to kind of stress the point for you between Fourier and response spectra. So this I stole off the internet just because I liked the way the other lecturer phrased it. And I think it phrases it better than I did in this slide here. So basically, Joseph Fourier, whose name the Grenoble University in France used to bear, he basically sorted out that any time series, so if I bang my hand on the table and you record that, or if you record my voice, or if you record an earthquake or whatever, any time series can be rewritten as basically a sum of almost infinite little sinusoidal waves. And of course, many people didn't believe him, but it's actually so. So I don't want you to know the math. I just want you to know that what he came up with helps us go from the time domain, you see delta t here, to the frequency domain. So it helps us take an accelerogram and create a spectrum. And what is the funny thing? That any random recording you can basically simulate by an infinite number of little sinusoidal waves with a different amplitude and a different phase, and of course a possible phase lag. So this is what a sinusoidal wave looks like. So imagine you have this and this, which is higher frequency, and that, which is higher frequency. The superposition of all of them is going to look like that. You can see it, it's not random. It's only made out of 3. And which 3? If you apply the Fourier transform to this time series, it is going to spit out these 3 frequencies, with their respective amplitudes. So it's going to tell you it's made up of these 3 frequencies, but real motions, like ground motion we record, they look like this. And of course, they include not just 3, but all of the frequencies. How much of each? This is the magic of the Fourier spectrum. If you make the Fourier spectrum, and we're only going to look at the amplitude, not the phase here, it tells, okay, it can't compute the very, very small frequencies, so ignore this. And it's telling you, okay, 2 hertz, this is how much energy you had. I don't know, 40 hertz, this is how much energy you have. 60 hertz, see, you've already dropped. And below 80 hertz, you know, you're killing it. So basically your signal is becoming noise. So this gives you a one-to-one representation of how much amplitude you have at each frequency. It breaks it up for you very nicely. The response spectrum does not. If you look at the response spectrum, which doesn't look like this, of course, and you say, 2 hertz, this doesn't mean 2 hertz of the Fourier. It means 2 hertz of the Fourier plus a wide range of frequencies participating in a particular way. It's not one-to-one, it's not linear, it's much more complex. The Fourier is honest, what you see is what you get. The response is convenient, but it's not exactly what you see is what you get. So Fourier amplitude shows us the change in amplitude with frequency, each and every one of them one-to-one. The phase, by the way, basically controlled where you have your maximum, but we're not going to care about it here. So this is what some Fourier spectra might look like in linear scale. So you can see pretty easy that it dies out after a point. You can compute it, but it doesn't have any energy left because the energy has died because of attenuation mechanisms, which we covered in the first class. And it's very edgy, very thorny. Usually we need to smooth Fourier spectra. And this was linear scale. And engineers mostly use linear scale, and I bet you might have been shown spectra in linear scale. Typically, we look at them in log, and that's where they acquire more sense. I'm just going to mention real briefly one slide for you to have in your reservoir when we have finished with all this. We assume that the source spectrum obeys a certain model. So the source spectrum of an earthquake. And when you record it at a distance, again, it obeys a certain model. So this is what we assume. And it's calibrated on a log-log scale, which is why we enjoy looking at Fourier spectra in log-log. We try and see whether they follow the model. So your acceleration would increase from 0 up to the earthquake corner frequency. It would plateau, and then it would start falling because of attenuation in the path and the site. So this is not about you memorizing any of this, but just knowing that I told you that a big earthquake generates low frequencies. So a big earthquake, you're going to find this here. It's going to go up real fast, and it's going to be rich in low frequencies. A tiny earthquake is going to go like this. It's going to take its time and reach its corner at a high frequency. So all of this, you don't have a lot of. See what I mean? You have a lot of the high ones. And whatever earthquake you have, you record it at a site, and this site has damping, and it's come from a certain distance, and that had damping. So from a certain frequency onward, it's going to die, and it's going to reach 0 eventually. So this was a real quick overview of Fourier, which we want because of reasons I'll show you in a bit. And quick reminder, whatever we record, like the things we just saw and analyzed with Fourier's transform, we record it at a specific site. Let's say I have an instrument on top of here, or at the top of this mountain here. I record something which has in it bits of the source, so some of the personality of the earthquake. Where did it break? How did it break? What type of fault? How much energy was released? Was it released into any particular direction, perhaps? What I record here also includes parts of the personality of the path. Distance, how long, how far away was it? Was the crust very healthy? Was it very fractured? Did it attenuate the motion more or less? And the heart of the matter here, which is the site. Am I on top of a hill? Am I at the flanks? Am I at the toe? Am I at the edge of the basin? Am I inside the basin? All of these little things. And why do we like the frequency domain so much? I keep going on and on about Fourier, about spectra, and about the frequency domain. This is why if I record something here and I look at the time series, by the way, time series is a little better than saying time history, which is the typical terminology, I'm afraid. The source and the path and the local site conditions, all of them together in the time domain are convolved. It's a mathematical operation called a convolution, and that gives you the ground motion here as a time series. And this is a little complicated, but wait till you get to the time domain. If you use these guys, if you use the Fourier spectra, then it's a simple multiplication. You can take the Fourier of the source, of the path, and of the site conditions, and just multiplying one with the other, you get the Fourier of whatever you recorded here, which includes the personalities of all three features. Why is this super cool? Because what we care about here the most is the difference if I build, let's say, in the middle of the basin, at the edge, right outside it, or at the top of the mountain nearby. So the ground motion at point 1 or point 2 is going to be a multiplication of the source, the path, and the local side effects. So imagine my source is quite far away. Imagine if you have this building and I have this, we're neighbors, right? We can walk to each other's buildings. And imagine we feel a magnitude 6 earthquake from, I don't know, let's say 100 kilometers or 50 even kilometers. These two are practically co-located with respect to how far the earthquake is coming from. So can you imagine in these multiplications, which of these parameters stay the same and which are going to differ, and how we're going to take advantage of Fourier's awesome discovery? Let's start from the source. Should it differ between the 2 points? Oops, trying to find my text here. Thank you. Somebody put me out of my misery by saying, no, yeah, it'll be the same. Thanks, folks. So whatever happens in the source stays in the source, pretty much like Vegas, right? So that's 50 kilometers away. It's the same for both recordings. Let's go to the path. Do we have the right to assume that the path is pretty much the same? Or is it going to be significantly different? Roughly is a key word. Thank you, Hamdi. So the local soil conditions are going to be the key difference, the key differentiator. So what happens if I draw a line here and there and I create ratios? Remember, we've been talking about ratios a lot. So let's go. This house, let's say your house, is outside the basin, and this is rock. So this is going to be our reference site. Remember, when we did our 1D, this was our reference site at Unity, and we're going to try and see how we can compute my little the amplification where my site, where my house is. So this little thing with the peaks and troughs that we computed before by hand, this is trying to compute it by data. So we have recordings here at my house and recordings at yours. What if we compute the Fourier and we divide them? This is going to take care of the source and the path, and it's going to leave us with a ratio of the local site conditions. Yours is on rock, so basically this is going to be my transfer function. This is going to be my amplification function. dividing this with that in the Fourier domain is going to give us a function of frequency, like we're used to, like we computed, and that's going to have ups and downs. We're going to see it a bit later. And those ups and downs are going to express precisely the effect of all of these layers beneath my house. And because this is not 1D, this is layers coming, you know, each and every way, and lateral discontinuities and what have you. So waves are going to be coming in, diffracted, refracted, surface waves, I can't compute this, you know, on my little piece of paper with 4h over Vs. So I'm going to turn to the data to tell me that, right? And well, just to be sure, where would you rather have your house? Where you have it or where I have it? Little typo here. Okay, Rockside, cool. And by the way, when I say I record something that's a convolution of source, path, site, I lied just a little bit, because you need to know that it's also a convolution of whatever little machinery I'm using to record. So if I had this really old recording station, which folks still show in the news nowadays, indicating how retarded we are as a country, and a really new, nice, expensive instrument, which could even fit in the palm of your hand, those two will not have the same response. And just so you bear in mind, there's ways that seismologists, of course, correct for that. But if you see the recording, it's also going to include a little bit of the personality of the recording station. This is just a little FYI. And to make it very clear, I just thought I would show you how the recording station personalities differed in the little lunar seismometers that this astronaut unloaded, I think in '69, or when was the first Apollo experiment on the moon. So it was working in the 70s, and this is a recording from April 71. We had a short period and a long period instrument. So this is what they record with frequency. And you can see that the short period, meaning high frequency, is recording out to 10 hertz, while the long period, meaning short frequency, kind of gives up after 2 hertz. So I think that's a little more exciting because this is something that actually was recorded on the moon in the 70s, and we don't have any other recordings after the 70s from the moon, which is a pity. And it can show you the very limited capabilities of sensors there. But just as we have better sensors now that can take you out to 100 hertz or more, you still need to be aware of what sensors you have and what limitations they have. So that's also going to feed into whatever you record, just FYI. And now, just looking at Fourier spectra, I think we've seen these before. So with period, I have the right to draw them with frequency or period, doesn't matter, one over the other. But what's the difference with the response spectrum? Just to remind you, on the Fourier, it's the pure frequency. So at 2 hertz, what is the energy? At 4, what's the energy? When you look at your response spectrum, you put on your engineering hat, that's what this was supposed to mean, and you think of a structure. It might be the lollipop thing, like this. I found these cocktail thingies for you to be able to show you like different period 1 single degree of freedom oscillators. So you think, is it taller? Is it shorter? Is this part, does it have more rigidity, more stiffness? Is the mass different? So this part. So based on that, you have your oscillator period, and that's what you see on the x-axis of your response spectrum. Whether it says frequency or period, it doesn't matter. It's the oscillators. Whereas on the Fourier, it's a different thing. So this is just to remind you where this is coming from. I taught you the Fourier, the response, you definitely know, you don't need me to teach you that. So this is just the slide for you to have there. And just reminding you that just like you've been taught this about structures, but this is the same about the soil. So the soil also has, we assume it's got like, its first degree of freedom, and then it's, so moving fast to a second degree of freedom and even higher degrees of freedom. And we already saw that. We saw a fundamental frequency, a first higher mode, a second higher mode, and they keep coming at higher frequencies. So we're not assuming this is one, but we're looking at the finer structure details. We're looking at it story to story, just like we might look at the soil profile layer to layer. So all of those details and how much this story moved with respect to the previous one, or this with respect to the previous one, that is shown in your amplification transfer function through the higher frequencies. The first one is this entire structure. How does it, how does it respond? And the primary, the fundamental way is this. The second way is this, the third way is this, etc., right? So just to get the feel that it's similar between soil and structures, we have the fundamental mode and the higher, meaning higher frequency ones. See, first one, second, a little more complex and curvy, third one, more complex and curvy. And what increases as you increase this? Frequency increases, right? Now, and of course, response spectrum, it's always characterized by a damping. And we said you have 5% for reinforced concrete, different kinds of dampings for different kinds of materials, fine. You can find like your 2-story or your 10-story or your, 50-story building, different locations of the response spectrum. Of course, also we said that for the Fourier spectrum too, if you see that you have a peak, let's say here at 10 hertz, you can think back and think, who's it going to affect? But your response spectrum is going to be mixing up the frequencies a little bit, but that's what's going to be talking about oscillator frequencies more. So just to have a look on the response spectrum, you have the maxima of all of your time series at different oscillator periods, right? Shorter to higher. So shorter period means richer in high frequencies. This is what you would have if you were looking at your PGA, so at your ground motion. Short oscillator, tall oscillator, you get richer and richer in long periods, and you lose the high frequencies out to where you actually just get displacements, right? And you can move from displacement to velocity to acceleration in the spectral domain just by shifting up or down by omega or omega square. So basically considering what your frequency is. So through your x-axis and without much need of anything else. So you have your acceleration spectrum, what it would look like in velocity. So starting from 0, displacement, etc. So moving between them through your omega, your circular frequency. Now we've seen that there's also vertical motion, but we've seen already and we've established that we care about the horizontal motion the most because of the S waves. S waves, they last longer, they get more amplified from the soil. The structures are more sensitive to them. In shaking in the horizontal direction, they're happiest under vertical loading like the dead weight, etc. And through the response spectra that we've looked at and defined, what are some of the peak metrics, which are basically intensity measures, which we care about in earthquake engineering? So obviously the PGA, first thing anybody's going to ask if they're not a seismologist, because the seismologist is going to ask, okay, if there was an earthquake, what was the magnitude? We're going to ask, what was the PGA, perhaps? I mean, it might be my first question if you say, I have a recording. Okay, what's the PGA? And that's more related to Newton's law, as we said last time, to the base shear that your building's going to feel. It's also a single number rather than a graph, so easy to communicate. It also gives us an idea, by the way, about whether we may or may not expect to have nonlinear effects in the soil. And we'll have 2 slides on that at the end. And if we don't get to go through them together, you're going to have them all to yourselves when you're at home studying. And PGA is, as you saw before, PGA, we take it from here. What characterizes this ground motion? High frequencies, which tend to disappear as we move to the right, as we move to velocity and displacement. So PGA is related to high frequencies, not just one. We don't know which one gave it to us. Okay. Now, PGV, peak ground velocity. It's really useful. It's not the first thing we mention, but it's the most useful for you guys if you care about damage and structural response. There's a lot of empirical correlations between damage and PGV. Also CAV, which is the cumulative absolute velocity, which is a more complex metric to compute. You don't pick it off a graph, you need to compute it, but just to keep it in mind. And velocity converses with longer periods, so somewhat lower frequencies. But it requires a bit of processing, so it needs you to filter out some of the lowest frequencies, which may be noisy, so that you don't feed it with too much garbage. And this is what a velocity pulse might look like. So sometimes you care about it because your motion, if you take it from acceleration to velocity, it might be just pushing your structure with one giant pulse. We have that a lot if we have directivity effects. So if we're close to the source and the earthquake is kind of coming our way, the rupture's coming our way. The Landers 92 event is one of the most famous ones for that kind of directivity. So there are reasons why we might care a lot about the velocity pulses. And also we might care about the peak displacement. Folks heavily into performance-based design might care about that because it's representative. The only trick is you need to have a bit of seismological training to get it right. So if you don't filter and you go from acceleration to velocity displacement, you will often get this. So this is practically screaming, please filter me, filter out the very low frequencies. And you can start filtering them out and eventually you get it right. And then you can compute, used on this time series, you can compute a lovely, wonderful response spectrum of the displacements. You may have taken out a little bit of the lowest frequencies, but usually this is how it's done in order to get a proper motion for displacements. So this we've already gone through, our rules of thumb. So n by 10 for a period of a RC structure, 10 to 10 basically 2 orders of magnitude worth of frequency range that we usually care about. A few corner frequencies for typical magnitudes, just to show that magnitudes 5, 6, 7, so the strong magnitudes are within the frequency interest, and also 4, it's gonna bring us up to 10 hertz. So 4, 5, 6, 7 have corners where they reach the maximum plateau I showed you, which are within 0.1 to 10 hertz, the range we care about. Very small events, of course, go to very high frequencies, and we already don't care so much about them. So I'm thinking you can have a quick stretch, and I think that if you're doing okay, I would like for the stretch to be less than 10 minutes. Would 5 do it for you this one time so I can release you on time? Because you have another class 10 minutes after we finish ours, from what I understood from one of your colleagues. So if it's okay with you, I'll see you at 6 past to start looking at our last few slides together. And I'll stop sharing until then. All right. Hello again, one last time. Okay. We had our stretch, and let's go to the last little part. How do people estimate site amplification? You already got to have a sneak peek of all of the methods, and we're just gonna kind of give the groups and give a little more background about them. So empirically, as we saw, through damage distribution, through observation, so what we call macroscopically, instrumental, which nowadays we also sort of call empirical, so through recording data. So when I was telling you my house is here and yours is there, and we have instruments, and let's divide the Fourier spectra, and theoretically or numerically. So the theoretical part, very roughly, is what you did with your piece of paper and pen when you did the 4H over VS, etc. That's theoretical, 1D theoretical with a lot of assumptions, so single layer over bedrock, horizontal, etc. And if it's more complex, like in this case, numerical. So use your computer, create a finite difference or a finite element grid, and give the material properties and geometry, and let the computer do the talking. Because of course there's no closed form solution in those cases. So empirically, I gave you a hint of what we do if we have data, meaning recordings. We divide spectra. And there's two ways we can do it. We can divide spectra on soil with spectra on rock, which is the ideal thing to do, because that's really the definition of the transfer function we learned the first day, which is basically what is the difference of the motion on soil with respect to the rock. But we don't always have, of course, a borehole or nearby rock. So we can also use another method, which is dividing the horizontal with the vertical spectra at the problematic site, at the site under study. So let's have a look at how that would look. So what we call the SSR, the standard spectral ratio, and that was also what was defined, discovered or introduced first. You have your, let's say, your suspicious site in the middle of a basin or on top of a hill, so where you would expect amplification. And you have your reference site where you don't. So either on rock outcrop here, or down here if you had, of course, paid a lot of money to drill and install an instrument in the borehole. So you have your recording, and you see the time series. You compute your Fourier amplitude spectrum. You smooth it, because it's really jaggedy. You smooth it, and you divide the two. Which one? The suspicious one to the divided by the reference. And that's going to give you a ratio, a spectral ratio, which is basically starting from 1 and telling you, okay, with respect to me, the reference site, how much are you, the soil site or the, I don't know, hilltop site, amplifying motion? How much, x-axis, and at which frequencies, y-axis? So we try to constrain these peaks. And of course, we assume that what we record on rock is unaffected. So why can we do that? We said it. The source goes away, the path goes away, because the source was further away from us, and the two of us are considered as co-located. And I end up with the ratio of the site of the local soil parameters. Now, if I don't have money to pay for a second sensor, I only have money for one sensor, I put it where the problem is, and I divide the horizontal motion with its own vertical. And this time I take its own vertical as being, by virtue, a little less affected by the horizontal. So I name it my reference. It's so-so, but it's been shown to be much, much better than not knowing anything. So we call it H over V most of the time. So an H over V on rock is going to look like this. So what I promised in the beginning, so more or less flat horizontal line close to unity. So that's saying what? if you put your station there and you see this, oh, that's rock, cool. So this might be a reference station. And I don't expect too much amplification here. Or if you put it somewhere, you put your sensor and you do your H/V, and you find this situation, so the top panel, it's like, whoa, dude, there's a lot of amplification, and where is it? If these are 10 events, and I get these H/Vs for the 10 events, I'm gonna get the average, and that average is gonna give me one peak, maybe a second one. So here it's saying what? This is 1 hertz, 2, 3. So close to 1 to 3 hertz, something is going on. If I get the average, I'm going to know more about it. So if I want to use the station as a reference, so this station here, for example, if I want to put the instrument and say, I'm going to divide everything with you because you are my reference, you're perfect, I might do an H/V there and just, you know, ask the reference station to put its money where its mouth is and compute the H/V and say, okay, are you close to unity enough? Yeah, 1/2 to 2 is pretty much close to unity because this is nature. So if so, yeah, I can divide with you and you can be my reference. Yay. So this was an example again from the one Greek city the foreigners among you are going to learn from me, I'm afraid, Aegeon, because it happens that that place is the one I studied the most. So we have instruments everywhere. So this is cool. We can see how the ground motion increases. These are the Fourier spectra, and I can do both. I can do top to bottom, and I can pretend not to see the bottom, and I can do H/V at the top. So what does that look like? Top to bottom, that's the best. You can tell it's the best because it's the most expensive. You need 2 sensors, right? So what is my resonant frequency? Oops, sorry. Anybody can basically guess that. Is there anybody who thinks that the resonant frequency is not 1? Good. So resonant frequency is 1, and higher modes are found 2, 3, 4. Why not 3, 5, 7? Because there's a hell of a lot going on. It's not a simple layer of a rock. It's a lot of layers. There's also inclined layers, and it's a mess. So all of the layers on top of the main rock interface are resonating at 1 frequency. That's a pretty low frequency. So pretty long period, 1 second. H/V, it shows me exactly the same frequency. That's why it's great. What it doesn't show me is how high the amplitude really is. So I have an amplification of up to 8. The Eurocode would have given you 40% or 45%. This is 8 times, 800%. The H/V would have given you 3 or 4. Okay, it's a good indication. But if you pay more money and you have an extra sensor, you get to anchor your plot on the y-axis. If you don't, you can expect to, you pay your money to anchor it on the y-axis, x-axis, sorry, on the frequencies, which is pretty awesome compared to nothing. So for spectral ratios, just a few little secrets or notes. You don't do one event, you need a few earthquakes, maybe 10 or more, and you get an average. That's when it means something. One on its own doesn't. As we said, this is what a spectrum looks like. If you start dividing with these huge troughs, it looks like, you know, something is dripping water. It's not going to make sense because the drips are like 1 or 2 orders of magnitude long. So you smooth it and then you divide. You use signals which are good, so good signal to noise ratio. If this looked like nonsense, you wouldn't use it. It's the well-known mantra, garbage in, garbage out. And we average on the log scale. So log everything, added, divided by the number, and up to the, you know, the exponent. As we said, you check your reference site if you do an SSR, so that you don't have any weird behaviors at what you thought was rock, but maybe is not behaving as rock. You usually do it on the S waves. And of course, anything I told you about the instrument, because you divide recordings, you don't have to worry about that. The instrument goes away. So what if you didn't want a computer, you didn't have a code to compute Fourier, and you had a code, because you're an engineer, to compute response spectra? You could still do your ratio, but you would need to know, and you wouldn't need to smooth, because they're nice and smooth already, but you need to remember this thing we said. It's not a one-to-one frequency correspondence. So here, this is going to be drawing from various frequencies, whereas, so it's user-friendly, but it's a little bit of a mix, whereas the Fourier is harder to get at, but it's really honest. What you see is what you get. 2 hertz is 2 hertz, not 2 plus minus whatever. And if you get to very high frequencies, the response spectrum is just gathering maybe 5 and above and mixing everything. You're not looking at 100 hertz or 80 or 50. You're looking at a big mess. So sometimes, last little detail, I told you that if you were walking along the slope here in Aegeon and there was an earthquake, the topographic effect, if you were walking like this along the slope, the topographic effect would sway you right to left. Similarly, more than front to back. And similarly, if you were walking, if you had a romantic walk close to the beach, because this is the water here, and there was an earthquake and you were at the basin edge, because you have alluvia all underneath you at the basin edge, then the ground motion would be stronger in the way you were walking compared to the right-left. So one phenomenon, the topography, sways you one way more, and the basin edge effect sways you more the other way. So this is just showing you that the ground motion in this direction, parallel to the basin edge, is more amplified than the one, let's say, in your along your cross section. And this has been shown numerically and also empirically, and it's true of, I think, of all basin edge configurations. So, because I don't want to go too much into wave types, I will tell you that I think a really cool thing with spectral ratios, and I think because you come from an engineering background, it might speak to you too, is that we can install sensors and understand the response of buildings. Last period, I showed you the results of Oliveira from Lisbon, and I told you that he did microtremors on 100 and something buildings, and he can actually vouch for a building with this height having that period. How does he know it? I told you he did microtremors. This is what he did. He put seismic instruments on top and at the bottom, probably. I haven't read that paper, but that's how you do it. And you record the background noise. Maybe you can't wait there for days or weeks or months to get earthquakes, but you can record a few hours and you record noise. And if you get the Fourier of the noise and you divide horizontal to vertical, and sometimes also it works with top to bottom, you can see a peak. And that is actually describing for you the fundamental oscillator peak of your structure. So this is a lighthouse in Rethymno, which is in central Crete. And folks from the observatory did that. So they also had to see the nice view there. So left the instruments for a while, and the H over V is giving them around 4 to 5 hertz, 0.25 seconds. And you could, of course, you guys have the talents and the knowledge to compare that to a numerical simulation if you wanted to, right? And you could see what that gave, and you would be able to corroborate it with instrumental data. So why noise? It's quick. You can do it in a few hours, even if it's a non-earthquake prone place. It's cheap. You take your instruments, you just leave them there. You stand by so that nobody steals them. You record, you solve a Sudoku, or you write your paper and you come back, you collect, and then you process, and you have this lovely peak. And that tells you about what kind of site you have underneath without having to pay any money to drill or to make any tests or take samples. So what you get from noise is pretty well correlated in terms of the frequency, but not the amplitude. So as we said, H over V in general, it gives you the first frequency, but forget about the y-axis. And of course, if you want something better and you know have the know-how and you pay and get the codes, then you can do 2D or 3D numerical simulations with finite what have you, or elements or whatever. And you can have a better idea. So this is again for Aegeon. So I'm again stealing from my own work. So this is what you get if you analyze this slope in Aegeon with the topography. So extra waves caused here, generated at the crest of the slope, you can see it here, and a ton of waves generated down here because of the various soil layers. So this is your input motion. It was just a little wavelet, not an actual earthquake. So you can monitor when the motion comes in, and all of the rest, if you turn your head, you're looking at time. So all of the rest is additional motion created because of this weird, this complex layering and all that. And this you can see in the frequency domain as well. So this is basically your amplification function in 2D, like 100 amplification functions for each of these little points put together. And you can see, for example, down here, this is close to 1, so it's your 1 hertz that we computed here with the H to V, and up there it's higher, it's like 4, 5, 6 hertz because it's stiffer material, etc. One thing you guys might sometime do, if you have the know-how to do numerical analyses and somebody else does your empirical work for you, or if you learn to do it, you can compare the two and you can validate your model. So this is something we often try to do. So where do I have my real sensors? I'll put like receivers in my mesh, in my numerical mesh, and I'm gonna do the same thing, the same SSR, etc. And well, lo and behold, it looks the same because it was calibrated well and it was checked. This is one of the ways that you can check your results. I'll go through these real fast. So yeah, validation. This is what you would have had with your 1D. See, lower amplification. You still get your fundamental frequency, just like you can do it on a piece of paper, 0.9 hertz or 1. But the amplification, you can get it right with numerical modeling, if you know your model, or if you have recordings. Either way, if you spend a little more money. You can see the effect of the damping. Stronger damping is killing the higher frequencies, just like we saw it on our first key plot in our first transfer function. So low frequencies don't kill so much. High frequencies, the red is stronger damping, and it's affecting higher frequencies more and more and more. So this comparison, you could try to be validating your damping or this or that. So there's lots of ways to look at it. Your geometry or your soil properties are both together. So it's a lot of fine tuning to get a model to work. But these are all of the nice things that your model can give you. Now, reality is complex, and that's why we ideally need data or the model. Now, the design codes are what we already said, A, B, C, D. That's it, VS30, inferred VS30. Take a spectrum, pull its ear up and to the right to cover for a few of the amplifications in the softer materials. Maybe a bit of topography. Nothing on base and edge effects to date. So a lot of this knowledge is up to you to apply where and when you know it. And I'll leave you with a few very nice papers that you can have a look at, which propose improvements to site classification based on the H over V, so based on the predominant period. And I'll skip through to the Pitilakis one because it's from Greece and it's very recent. So this is a proposal to add more detail to the Eurocode table that we saw together. A, B, C, D, E. He respects that, they respect that, but they break the B into 2 different kinds, the C into 3 different kinds, etc. Why? Exactly because the VS30 is not the only thing you care about. You can have deeper alluvia, shallower ones, so you can have your resonance period change. So they grab on that and they build onto the seismic code to refine the current site classification. And that's something that you can have a look at on your own. And if you ever need to do it, they have proposed spectra. We'll wait and see. In a couple of years, it will likely make its way into the actual Eurocode 8. And maybe in a couple of years, we'll be teaching something slightly different and better. So that's it for me. And we've hit 11:30. And as I expected, the last few slides on nonlinearity are not going to make it into this last lecture, but I'm gonna leave them to you just to get an idea. So this is the last bit of the Kahoot, the one that I think nobody knew. So when you shake very strongly, just keep in mind that your VS or your stiffness decreases and your damping increases. If you compute the same transfer function for strong shaking, it's going to shift the peak right and left, and it's going to shift it up and down. So this is tied to soil dynamics, and 30 seconds are not enough to introduce you to this, but I'm going to leave it to you. And at the end of the day, I have here for you the little table that Eurocode 8 has on nonlinearity. So this is how stiffness relates to density and velocity. So that's why they're kind of, well, not exactly analogous, but they go in the same direction. So with that, I'll leave you be. You'll have these slides along with the previous ones on the platform you guys share. I'll stop sharing now, actually. You'll have the slides by Dimitris on the platform you use for slide sharing. You do have my emails at the beginning of the 2 PowerPoints. I do hope, even if it might have been a lot of info and maybe somewhat outside your comfort zone, I hope it was useful to kind of open your eyes to all the other things there are out there that soil does to us. And hopefully you can realize the limitations of what you can do and know the lovely tools there are and possibilities to do a little more. And a lot of what you can do can be done on the back of a pack of cigarettes with 4H to VS. That can get you in the right track just in 2 minutes. So you'll have a little bit of an exercise as an add-on to your term paper for a bit of extra credit. And I'm gonna see to that with Dimitris. I do welcome you to write to me with any questions about this material, about additional material, any kind of advice. If I can ever be of help to you, I'll be very happy to. If you're interested in a postgrad project or whatever, I'll be around. So it's been lovely reading you. I haven't seen you, I'm afraid. And I hope this was fun. For me, it was. And I hope you're all well and healthy and work hard and you achieve all your goals. So take good care. And that'll be all. Bye-bye from me.
Thank you.
Thank you very much.
Thank you very much. Have a nice
Thank you very
day.
much.
Thank you very much. Bye.
Have a nice day.
Thank you very much.
Bye. Bye.